Hi guys, it's George again. Alright, so in a previous video I went over the second law of thermodynamics, and in that video I explained how heat transfer has a natural direction in which it likes to flow in, and that direction is always from hot to cold. In this video, I'm still going to go over the second law, but now I'm going to be focusing on the concept of entropy. And entropy is one of the most important and useful tools that we use to understand thermodynamic systems, but I've seen a lot of people struggle with this, and that's why I decided to dedicate an entire video just to this, so that we can really get our head around this. Okay, so the second law states that during any natural process, and by natural process I just mean any process that could occur in nature, the total sum of entropy of the system must increase. We also call this the increase of entropy principle, but before we can truly understand this statement, we first must understand what in the world entropy is. So I'm going to explain that now. Okay, so entropy is usually described as chaos or disorder, and I'll explain why. Let me take out a picture of states of matter. Here we go. Okay. Now, the reason why I'm taking this out is because when we're talking about entropy, what we're really talking about is we're talking about all possible microstates that a molecule can have. And whenever I say that, people freak out and they say, like, I'm never going to understand this. It's really not that bad, but it does take some thinking to understand what's going on. Okay, so in a gas compared to a liquid, there's more motion in a gas, right? The molecules have more freedom. There's more things that they can do. And the same is true when comparing a liquid to a solid. The liquid molecules are arranged in a way that they have more freedom than a solid molecule, but they have less freedom than a gaseous molecule. Now, when I say all possible microstates, I mean, let's take a look at this molecule right here. Since this is in a gaseous form and it has more freedom than the liquid molecule, then that means that this one has more possibilities of where that molecule can be located. There are more possible microstates. That's what I mean by microstates. This molecule here, has less freedom than this one. It has less range of motion. And when comparing the solid to the liquid, again, if you look at this molecule has less possibilities, has less range of motion than this molecule. So that's what I mean when I say the word entropy. I mean, what are the possibilities that the molecules I'm talking about could be in? The more possibilities, then the more entropy. And so I guess when we're talking about entropy, we're talking about how easy is it for us to predict or understand the motion of the system. It's a lot easier for us to understand the motion of a solid because it has less possibilities. And it's a lot harder for us to understand the motion of a gas because it has way more possibilities. Okay, now when talking about entropy, it's very important to remember that entropy is dependent on two things. It is dependent on heat transfer, and it is dependent on something called irreversibilities. Something like that. And I will cover irreversibilities a little bit later, but right now I just want to focus on heat transfer because this is important. Okay, now let's say that in this example we're talking about water molecules. So this is all water. So in this case right here, this would be ice. In this case, this would be liquid water. And in this case, this would be steam. Okay, now what happens when I add heat into the system? When I add heat, and we're going to use the capital letter Q because that's the letter we chose to denote heat. When we're adding heat, remember that heat has the same units as energy. They're all kilojoules. So heat is the exact same thing as energy. So we're adding energy into the system. That energy is going to be absorbed by the ice molecules, and it's going to be translated into kinetic energy. It's going to be translated into motion. So these molecules are going to be moving around more. And remember that I said that entropy is the total number of possible microstates in a system. So before I added the heat, this had a certain number of microstates. It wasn't moving around much. But now I add heat, I add energy, and that's making the molecules move around more. And therefore, the entropy of the system is increasing. And eventually, when you add enough heat, you're going to cause a phase shift and it's going to turn into liquid water. And remember, liquid water, the molecules for liquid water have more range of motion. They have more energy. They have more freedom than the solid molecules. And therefore, the liquid has more entropy than the solid because the possible microstates went up. And the same thing would happen if I keep adding heat to the water. Let's say I add more heat to the water. That's going to increase the energy. It's going to be translated into kinetic energy. The molecules are going to be moving around more. Eventually, I'm going to have a phase shift and I'm going to turn into a gas. And these molecules have more possibilities. They have more possible microstates. And that's why we say that entropy is the same thing as chaos or disorder. Because here, the possibilities are a lot larger than over here in the solid. This system, we could say, is more chaotic. There's more disorder. It's harder to understand. And that's why we relate entropy to just being chaos. But it's important to understand that exactly what's going on. We just mean that the possibilities for the molecules in the system is higher. All right, so now we understand why heat transfer affects entropy. Let's talk about irreversibilities now. Let me go ahead and clear this. All right, so here we're talking about irreversibilities. Irreversibilities. Okay, now remember, we're talking about entropy here. So if entropy is going to increase, we're going to be talking about things that add randomness to the system. And that's exactly what reversibilities are. So these include things like friction, electrical resistance, and chemical reactions, mixing of two fluids. Okay, so these are some examples of reversibilities, and there's many more. But pretty much, irreversibilities are anything that would add randomness to the system. You add randomness to the system, that by definition increases entropy. So those are the two components that make up entropy. We have heat transfer, which increases entropy by increasing motion, and motion creates more possible microstates. And we have irreversibilities, which again increase entropy because they add randomness to the system. So now that is everything you need to know about what affects entropy. Now I want to talk about some of the sticking points, some of the things that makes understanding entropy a little complicated, or some of the common mistakes that I see people use when talking about entropy. Okay, now by far, the most common mistake that I see when dealing with entropy is not fully understanding the increase of entropy principle. All right, so that's what we're going to talk about now. So this is the increase of entropy principle. And it's understandable why people have a problem with this. If you just read the statement, it says that entropy always increases, but that's not actually what's going on. So let me take out my picture again. Okay, let's see. All right, there we go. Let's make it a little bit bigger. Cool. Okay, here's where people get caught up. People read the statement, the increase of entropy principle, and they automatically assume that entropy always increases. And that is not the case. This is very, very important. And remember earlier when I was saying that if I add heat to my system, then the number of possible microstates goes up, and goes in this direction, and then in this direction, and then these molecules have more freedom, they have more range of motion, they have more possibilities than this situation, and therefore entropy went up. But what people forget is that you can go in the opposite direction. You can remove heat from a system. Now what happens when you remove heat? Let's say that we're dealing with steam here, and let's say I'm going to cool the steam down. Then eventually I would cause a phase shift. It would go from a gas to a liquid. And while that's going on, I'm removing energy, I'm removing the ability for these molecules to move. And as I do that, the range of motion is going to decrease, and therefore entropy will go down. And we know from everyday experience, it is possible to turn steam to liquid and a liquid to ice. We know that it's possible. So we know it's possible for entropy to go down. So it's very, very important to understand that. Entropy can go down, and it relates to heat. You add heat, you add energy, entropy goes up. You remove heat, you remove energy, you remove possible microstates, and entropy goes down. Now, we have a question. Why in the world does this statement exist? Why does the increase of entropy principle exist? And that's exactly what I'm going to explain now. Here's where irreversibilities come into play. Okay, this is my favorite example to use to illustrate the change in entropy of a system. So let me go ahead and draw a piston. I'm going to draw a piston. And I'm going to draw this. Okay, and let's say we have some water in here, so I'm going to draw some water molecules. Okay, and now let's say we were to add some heat into the system. So add some heat, and I've illustrated this before. What happens when you add heat is that the molecules want to be in a state of constant vibration. They're always moving. And I'm adding energy into the system, right? So that energy is going to be transformed into kinetic energy by the water molecules, and they're going to start vibrating more. The range of motion is going to increase, right? Remember, this is why entropy has now increased, because I'm adding energy, I'm adding range of motion to the molecules, and thus I'm adding microstates, and therefore entropy has gone up. And this is going to make the water molecules bounce off these walls a little bit more than they were before. So I'm increasing the pressure inside this piston. Just like this. Okay. Now what's going to happen if I draw the new state here? So at the end of this, our piston is going to change. Our piston would have gone up because of the change in pressure inside the vessel. And let me just draw some water molecules. Something like that. Okay. So I added some heat. The water molecules absorbed that energy. They converted to kinetic energy. That increased the entropy of the system. And that also increased the pressure inside this vessel. Piston goes up now. Now, let's say that we started off with zero entropy, just for the sake of argument. So here we have zero entropy. And the letter they use to denote energy is actually not E. We use E for energy, so they just went with the letter S. So here we have zero entropy. In this situation, we know we added heat, we increased microstates, and therefore entropy had to have gone up. And let's just say it goes up to 5. So now we have 5 entropy. But this is not the full story. Remember that there's two components to entropy. There's heat transfer and there's irreversibilities. Now, as the piston was going up, there was friction here. There was friction at the wall, at the boundary. And this friction is one of those irreversibilities that was in the list that I gave you earlier. And therefore, this would not have gone up 5. It would have gone up more than 5. So let's say it went up 6. It went up 5 because of the heat transfer, and it went up 1 more because of the friction. And now, let's say we cool this down. Let's say we remove heat from the system. So let me just show that case over here. Let's see if I have room. Okay. So now we remove heat and my water molecules. Okay. Now, this is the progression. We add heat, entropy goes up, but there's friction. So entropy goes up a little bit more than just by what would have been caused by the heat transfer. And then we remove heat. Sorry, I forgot to put a Q here. We remove heat. We remove heat, And now the same thing happens. We remove heat, we remove energy from the system, we remove the range of motion of the molecules, we remove microstates, entropy goes down. So let's say it goes down it goes down by 5 entropy. It goes up 5 units of entropy. But again, this is not the full story. There was friction here as the piston was coming down, right here. So this would have caused, I forgot to use yellow. This would have caused it to go up 1 entropy. So what's going on here is that we're going from 0 entropy, up 5 from the heat transfer, up 1 more because of the friction. Then it goes down 5. So 6 minus 5 would be 1. But then it goes up 1 more because of the friction. So we started off with 0. We went up to 6. We went down 5, but we went up again 1. So at the end of the day, we end up with 2 entropy. And this is the increase of entropy principle. That at the end of any process, even if you add as much heat and remove the same amount of heat at the end, in theory, it should remove the entropy that you added. But because of the irreversibilities, the friction, mixing of two fluids, chemical reactions, you're always going to add some more randomness into the system. And at the end of the day, your entropy will always be greater than what you started off with. And this is the increase of entropy principle. During any process, this is going to happen. At the end of the day, you will end up with more entropy than what you started off with. Okay, now I just spent all this time explaining what entropy is, but I don't think we have a feel as to why we care about this thing. So that's what I'm going to do now. I'm just going to give you a short list of entropy applications. And these are just ways in which we use entropy nowadays so you can better understand why we care about this thing in the first place. Okay, so probably the most common and probably the most important way in which we use entropy is for something called efficiency. And why we care about efficiency makes perfect sense. We usually want to create systems that generate power, right? And it's very important that you understand how efficient these things are at. You're going to put some energy into the system, and that system is going to generate useful work out of it. And you want to know how good your system is at taking the energy you put in and creating useful work out of it. And no system is ever going to be 100% efficient. That's just not possible. But then that's why you have to calculate the efficiency. You want to find out how efficient it is at doing its job. And a very common calculation that we use in engineering is to calculate the isentropic efficiency. Isentropic efficiency. And when I say the word isentropic, what I mean is that we are assuming that this system is perfect, that it is 100% reversible, that there are 0 irreversibilities. Pretty much entropy change at the beginning, from the beginning to the end, is 0. And this breaks the increase of entropy principle. This is not possible. There is no real system that you can create that is 100% isentropic. But it's still important to do the calculation for 2 reasons. One, it makes the calculation very easy. It makes it very, very simple. We can do it very quickly. And 2, it tells you the maximum limit of how efficient your system can be. Because there's no way you can make it more efficient than if the system was perfect. So let's say you calculate the isentropic efficiency of your system, and it tells you something like 60%. It is 60% efficient at taking the heat you're putting into it and generating useful work out of it. When you actually build the thing and when you actually use it, because it's a real system and there are reversibilities in the system, that's going to create losses. And the efficiency that you actually get is not going to match the isentropic efficiency. If the isentropic efficiency was 60, you'll probably get something like 55 or 50 or something that's definitely lower. But it's still important to understand the maximum limit of how efficient your system could possibly be. Okay, another application of entropy actually deals with perpetual motion devices. Motion devices. So a perpetual motion device is a system in which you can turn it on with no power source, no anything, and it will run forever. And because of entropy, we know that this is impossible. There is no way that you could possibly create a perpetual motion device, and that's because of entropy. If you could convert all your energy to useful work with no reversibilities, no energy loss, no nothing, then theoretically it would be possible to create a perpetual motion device. But because there are reversibilities, there is friction, there is electrical resistance, you are always going to run out of energy eventually. And that's why you always have to have a power source when you deal with any real device. And people have been trying to make perpetual motion devices for centuries. And because of entropy, we know that this is pointless. You are never going to make one because entropy is always going to create losses in your system. Now, these last two are a little bit more philosophical, but I still think that they are important, so I'm going to talk about them. The first one actually deals with time. So there was a problem when dealing with time. We know from everyday experience that time goes in one direction, right? It always goes forward. And there's no way that we know of right now to go back in time. Now, when a scientist wants to say this, you can't just say that time goes forward. You have to be a little bit more specific than that. You have to clarify things very, very well in science. So they actually use entropy to denote the direction of time. We say that time always goes in one direction, and that direction, because of the increase of entropy principle, always goes in the direction of increasing entropy. And that's actually how we define the direction of time, or one of the ways in which we define the direction of time. Now, this last one is just fun. The last one deals with the end of the universe. And this is the idea that because of the increase of entropy principle, that means that entropy in the universe is always going up, right? And remember earlier I described entropy as just disorder or messiness or chaos, right? So what we're saying is that the chaos or the disorder in the universe is always increasing. The universe is always in a state of constantly becoming more and more chaotic. Right? And what some philosophers have been saying for a while is that eventually the universe will reach a state of thermodynamic equilibrium. It'll reach a state of absolute maximum entropy. And at that point, there is nowhere else to go. That means that this will be the end of the universe as we know it. It will cause a heat death of the universe. And if you're more interested in this, there's a lot of YouTube videos you can watch on this. It's actually kind of interesting. But yeah, I think that's everything I wanted to mention about entropy, and I will see you guys on the next video.